Hi, what we're going to talk about today is scientific notation. Scientific notation is a very convenient way of writing large and small numbers, and actually taking the product or quotient, in other words, multiplying or dividing those numbers. And I'm going to show you, hopefully, why that's the case. Hopefully, you'll agree with me by the end of our lecture today, and I'm going to show you a few examples. All right, so what scientific notation does is it takes advantage of using exponents or powers of 10. So for example, we all understand, hopefully, that exponents, so y to the third is just simply y times y times y. So when you write this, 10 to the third equals 10 times 10 times 10, which equals 1,000. 10 squared, we call our 10 to the second power equals 100. 10 to the first equals 10. So this enables, if you realize this and realize that you can multiply times one of these numbers, like 10 to the third, 10 squared, you can write large numbers in very compact ways. And these are maybe not the best examples because these are not the biggest numbers, but we're going to get to some later on where it is more obvious what the advantages are. All right, so for example, 5,000, I hope you can all, without a lot of explanation, understand that 5,000 is equal to 5 times 1,000, okay? And 1,000 is equal to 10 to the third. And we know that because 10 times 10 is 100. That would be 2. And then 10 times 10 times 10 is 1,000. So as you see up here, 10 to the third equals 1,000. So 5 times 1,000 equals 5,000. And that's going to be equal to 5 times 10 to the third, which is what we're looking at here. That's the result that we're looking at. So that is commonly referred to as scientific notation. And you can see the same thing in the next example, where in this case we added a few digits after the 5. So in this case we have 5105. Again, it's equal to 5.105 times 1,000. And that 1,000 we're just going to write as 10 to the third. Okay? Very easy to understand. And one of the nice things is when you have numbers greater than 1, it's always easy to understand what power you are by counting the zeros. So for example, I'll just write a quick example up here. I'll do this in blue. If you had a number like 1, 0, 0, 0, 0, 0, 0, we just count the zeros. 1, 2, 3, 4, 5, 6 zeros equals 10 to the 6. Okay, this is a million equals 10 to the 6. You'll see when we get numbers less than 1, you can't really count the zeros. Or there is a kind of a trick of doing that, and I'll show you how that's the case. All right, so let's look at numbers less than 1. So in fact, you can't have 10 to a positive exponent, positive power, and come up with a number less than 1. Obviously, we need to use negative exponents. So that's what this says here. It's a little bit obscured by our splatter here, but that is y to the negative third, which you probably know from your previous experience in math is equal to 1 over y to the third. So a negative exponent means just take a fraction and then apply the exponent in the denominator. So that's going to be equal to 1 over y times y times y. So we can write these the same way as we did with the positive powers. 10 to the negative first equals 1/10 equals 0.1. 10 to the negative second equals 1 over 100 equals 0.01. 10 to the negative third equals 1 over 1,000. In other words, 1 over 10 to the third equals 0.001. And before we were counting zeros, you remember, to figure out which power we're at. You can do the same here as long as you include that 0 to the left of the decimal point. So if I write a number like 0.000, I'll stop there. 1. So how many zeros are there? There's 1, 2, 3, 4 equals 10 to the negative fourth. Oops, negative fourth. Okay, so that's 1. Oh, and if you count if you look at this, this is the first one would be 1/10, 1 100th, 1 1,000th, 1 10,000th. And as you know, 10 to the fourth equals 10,000. So the fraction having in the denominator would make it 10 to the negative fourth. So that's how we know how to write those. So we can do the same thing we did here as before when we had positive exponents. 0.05 is simply going to be equal to 5 times 0.01, which hopefully you are following that. And then the 0.01 we know from, well, we can see it up here. In this case, equals 10 to the negative second power. Okay, and you can do that by, again, counting the zeros, or by realizing that 10 to the negative second is 1 100th, which is exactly what we're looking at here, 0.01. So we're going to do the same here, and the additional numbers here, 105, kind of just come along for the ride. So you end up with 0.05105 equals the product like that, and then it equals that, which is essentially in scientific notation. So it's probably not obvious to you yet why this is a value. We're going to come to an example later to explain that more, but I wanted to run to, before I do that, I want to also let you know that you can use, and you will frequently see people that will write it, instead of using the common notation like this, times 10 to the third, for example, 1.1 times 10 to the third, they'll write something like this, 1.1 E3 with lowercase or uppercase 3 after that. So that E, simply as it says here, it just means 10 to the power of. So 1.1 times 10 to the power of 3 in these cases. And you'll see this, for example, when later on in the course, when we're beginning to use Excel, Microsoft Excel spreadsheet, when you want to write a number with an exponent, you're going to have to do it like this using the E. All right, so now we're going to actually run through two examples, not too different from the examples we already showed you in the previous slides, but I want to just walk you through step by step, make sure everybody understands how it's done. Okay, so in the first case, I'm going to write 0.0051 in scientific notation. So I'll simply write that out here. We have 0.0051. So we're going to write this in scientific notation. First thing we need to do is break this into two pieces. So it's going to be equal to 5.1 times, and then where is this 5? Here's our decimal point. So it's 1, 2, 3 places over. So it's simply 0.001. And then we know from basic mathematics, this is the 1/10ths column. This is the 1 over 100th. This would be 1 over 1,000. So 1 over 1,000 is 1 over 10 to the third, which equals 10 to the negative third. So we can simply write this as 5.1 times 10 to negative third. Okay, it's easy as that. Same thing down here. In this case, we're going to have 5,100 is what we're starting with. And again, we can break this up into two pieces, 5.1. And then we can write, in this case, it's in the 1, 2, 3, 4 columns over to the left of the decimal point. So times 1,000. And we know 1,000 equals 10 to the third. We can get that just by counting the zeros. 1, 2, 3, 10 to the third. So the result is 5.1 times 10 to the third. And that's basically the solution. You can write this if you want. Sometimes you'll see a number like this where it'll be like, this is the same number. It'll be like 0.51 times 10 to the fourth. Okay, and I'll leave that to you to understand why these two numbers are essentially the same. Try and work that out yourself. All right. Next. All right, so here's the case, just an example of something you may encounter when you're in chemistry or physics class. And you're looking at how many, essentially Avogadro's number tells you the number of atoms in this unit called a mole. I'll write it out here, mole. So mole is just the particular number of atoms or molecules that constitutes this thing that we commonly refer to as a mole. So you can see here, here's the number when we first write it out as in sort of a conventional number. And then I'm going to break this into two pieces, and where it's a product of the 6.022 and this large number. And then you can count the zeros if you like, and what you'll find is that there's going to be 23 of them. So that's going to result in 6.022 times 10 to the 23rd. All right, so that's just one example of many that I could show you in either physics and engineering, chemistry, where scientific notation is very convenient, because you're not going to want to have to, every time you do calculation, write out this very large number. You know, it's error prone, and you just don't want to do it. It's tedious and takes up too much space. All right, so frequently you'll get like two numbers in scientific notation, and you'll want to either calculate a product, or which is just multiplying, or you're going to want to divide them. So there's a very simple way of doing that. Remember from rules of exponents that here's the rule. Essentially, y to the x times y to the z equals y to the x plus z. In other words, you just sum these exponents. All right, so we can also say that if we took 10 to the x, for example, and I'll just write it out here. So 10 to the x times 10 to the y would equal 10 to the x plus y. Then moreover, you know you can, if we're multiplying two numbers in scientific notation, you know by a law of, I believe it's commutation, commutivity, you can, the order that you multiply these things doesn't matter. So you can, here's one scientific number in scientific notation, r times 10 to the x. Here's another one, s times 10 to the z. And you know you can change the order, so we can write it as r times s times 10 to the x plus z. And in this case, to get 10 to the x plus z, we basically invoked this rule here. Okay, so that's how you do that. Same deal with quotients, x, and I'll just skip down to here. R times 10 to the x over s times 10 to the z. It doesn't matter the order in which we do the multiplying and dividing, so you can write that as r over s times 10 to the x minus z. So in this case, because the z is in the 10 to the z power is in the denominator, instead of adding the exponents, we subtract them. Okay, so that's the difference between a product and quotient. And here's an example where we have a product and a quotient. And you can look at this later on your own, understand what it is. But here's an example where we have r times 10 to the x sub 1 power. That x, maybe you're not used to seeing these, but you will see these a lot. It's just basically, this one is called a subscript. So x sub 1, x sub 2, x sub 3 are basically three kind of arbitrary numbers in this case. All right, so r times 10 to the x sub 1 over s times 10 to the x sub 2 times t times 10 to the x sub 3. So in this case, we're going to take the number, the sort of initial numbers from each of these and put them together. So r times t, then s is down here in the denominator. So we end up with r times t over s. And here's where it's kind of fun. We're just going to add and subtract powers. So it's x sub 1 minus x sub 2, because x, this one is in the denominator. And then because we're multiplying, then we're going to add the x sub 3, so that you can end up with a solution like that. So this can help you a lot when you're doing very complicated mathematics, and make sure that you can do kind of approximations in your head to help you with handling handling these and also knowing that your result looks kind of right rather than relying on your calculator and typing in long numbers. All right, let's go to the next slide. This is a case where we want to find the mass of 1 mole of carbon atoms. And we know two things. We know that one carbon atom has this mass, 1.9944235 times 10 to the negative 23 grams. So that is like a really small number. Imagine multiplying 1/10, 20 together against 1/10 times 1/10 times 1/10, 23 times. That is a really small number. On the other hand, the number of atoms in a mole is this very large number, 6.022 times 10 to the 23. We saw that before. That's our Avogadro's number. So you know how heavy, or the mass of one atom, you know how many atoms you have in a mole. If we take the product of the two, in other words, if we multiply the two, we're going to get the mass of 1 mole of carbon atoms. So I'll write that down, mass. Let's do this in black. All right. So the mass equals, and I'm going to do a little round off here. I hope you don't mind. 2.00. That's not right. That's not the right round off. We'll do it right. It's going to be 1.99 times 10 to the negative 23 grams. And I'll add a little subscript here, or not a subscript, a denominator in the units. So it's grams per atom, right? Just so we kind of have in our mind what we're doing here. And then I'm going to write here 6.02 times 10 to the 23rd. And I beg your pardon, but I've run out of room here. So I'm going to write it here. I'm going to write atoms per mole. All right, so we're multiplying this number times that number. So we can regroup these. We can write equals, and we can also cancel our units here. So atom cancels out with atom. We're going to end up with grams per mole, right? So we're going to end up 1.1 1.99 times 6.02 times 10 to the negative 23rd plus 23. Okay, because negative 23, and we're multiplying this. This one had a positive 23. And as you can see, that's just going to be 10 to the 0, which we know to be 1. And then I'll do I don't want to get my calculator out. I'm lazy. I'll just say that's kind of 2 times 6, which is about 12, which is about close enough for me. We're going to end up with 12 grams per mole. And I'll leave it to you to go to the periodic table and confirm that this is the atomic weight of carbon, which in fact it is.